Hey guys, in this lesson we are going to be studying the molecular formulas and their masses. And we'll also cover the empirical formula. We'll do a couple of different things. We'll be able to solve for the empirical formula and solve for the molecular formula. This is the more challenging one in the lesson, so keep a little brain power ready for this part, and then we'll have class practice. The bookwork associated with this lesson is 7 through 15 on page 30. So please write that down on the very top of your classwork page and follow it with our aim. What are empirical and molecular formulas? After that, please write these do not questions, but don't answer them. I'll correct the formatting now. All right, so molecular formula and molecular mass. A molecular formula is simply the formula for a molecule or covalently bonded substance. Therefore, molecular mass would simply be the mass of one formula unit for that molecule. We can find the mass of a molecule by simply adding up the individual masses, the atomic masses, of the atoms in the formula. So for instance, if I wanted to solve for the mass of water, H2O, I would need to add up the mass of 2 hydrogen atoms and add to it the mass of 1 oxygen atom. There is an organized way to do this, represented by the table that you see below. I'm going to fill in some data and then I'll come back. Okay, so if you look on your reference table for the mass of hydrogen, you'll probably see the value 1.00794. Additionally, for oxygen, you'll see the value 15.9994. These are the atomic masses for the elements, but what I'm going to tell you right now is going to save you a lot of time. Because these elements differ from the whole number, the integer number of 1, and in this case 16, they differ so little from that integer number that it's not going to affect our answers if you just round 1.00794 to a 1 and 15.9994 to a 16. I promise it really won't affect your answer, and it will make your life a lot easier to do this rounding in these types of questions. So in any case, what I did was I took the mass of an individual atom of the element and I multiplied it by the quantity of that element. For hydrogen, their subscript of 2 told me that there were 2 hydrogens, so I did 1 times 2 is 2. And then for oxygen, I did 16 times 1 is 16, because there is only 1 oxygen atom. Now I will need to do an ultimate sum, like to sum everything together, and it's in this case, it's 2 plus 16. And 2 plus 16 does, of course, mean 18. And the unit that you could put for this, for today at least, is AMU, atomic mass units. We will have other units for that later, but that's for a later lesson. So empirical formulas are the smallest whole number ratio of elements in a compound. I'll give you that definition in a second, but it is really important for ionic compounds, like NaCl, where you have a metal bonded to a nonmetal. They tend to form these really highly ordered structures called crystals. And the size of a crystal is actually unlimited. You can see here that I put in several little squares of crystal just to show that you can keep building them on top of each other, and there's no reasonable limit for where the crystal would have to stop growing. The reason why I'm bringing that up is because a molecule or a molecular formula does rely on the molecule having a definite size. Like it has to have like a certain size and it can't be larger or smaller. That's the only way you can write the formula for a molecule. But it's a lot harder to do that for substances that are ionic, because ionic substances form crystals and crystals have unlimited size. So I went ahead and wrote that in. You definitely need to have that in your notes. So not all hope is lost. We can still assign masses to ionic compounds. We just wouldn't be able to assign a molecular mass. Instead, we're going to assign a mass to the smallest subunit of the crystal. And that is the definition for empirical formula. So the empirical formula is the smallest whole number ratio Let me add that word in. That's a very important word. It's the smallest whole number ratio of elements in a compound, and we use it primarily for ionic compounds because they have unlimited size, but you should know molecules do have empirical formulas too. I'll prove that to you in this table down below. So the molecular formula for water is H2O, and the molecular formula for glucose, you might remember from living environment, is C6H12O6. The empirical formula for water would be the smallest whole number ratio of the elements in the compound. Right now, the ratio is 2 to 1, and you can't actually reduce that any further, so the empirical formula remains H2O. But for C6H12O6, the ratio is 6 to 12 to 6. And the greatest common multiple that they share is a 6. So if you divide all of those numbers by a 6, you can get the ratio 1 to 2 to 1. So that was going to be the ratio for the empirical formula. So carbon is going to have 1. I don't need to write a 1. I already wrote the C. The H will have a 2, which I don't need to write. And the O will be 1. So CH2O would be the empirical formula for glucose. So glucose is a molecule, and molecules have empirical formulas too, not just ionic compounds. All right, so here is a really easy thing we can do. We can take a molecular formula or an ionic formula and find its empirical formula. Right now, its ratio is 2 to 2. Greatest common multiple is a 2, so we'll divide everything by 2 and we'll get 1 to 1, which means that the actual empirical formula for this compound is HO. But it's a little bit harder if you need to solve for the molecular formula. There are some basic steps right here, which you can come back to later in the video if my explanation on the next slide still leaves you confused. So let's find the molecular formulas of the following. CH4 is going to be our first charge. So the empirical formula is CH4 and the molecular mass is 32. If you do a little bit of mental math, hydrogen is only a weight of 1, but times 4 would be 4 times 1 is 4. Carbon's weight is about 12, and 12 plus 4 is 16, which is nowhere near 32. What I'm getting at here is that the molecular mass, or the molecule, is much heavier than the empirical formula. And you also might remember that the empirical formula, it just is repeated and builds the molecule. These are like the building blocks for the molecule. So what I'm going to do is figure out how many of these building blocks will give me a mass of 32. So I'm going to officially calculate the mass of CH4 first. So in step 1, the carbon has a mass of 12, and there's only 1 carbon. And the hydrogen has a mass of 1, but there are 4 of them. And this gives me a mass of 16 AMU. The molecule has a mass of 32 AMU. And I know that the molecule is made of these building blocks, and all of the building blocks have a mass of 16. So I'm going to do 32 divided by 16 AMU, and I get the number 2. This means that there are 2 units of CH4 in the molecule. So in my third step, all I really need to do is multiply all the subscripts in the empirical formula by 2. And that's going to give me a formula of C2H8. Starting from CH4, multiply a 1 times 2 to get the 2, multiply the 4 times 2 to get an 8. And if you do some quick math on this, I won't bore you with it, but its mass is 32 AMU. All right, let's do another one. If the empirical formula is CH3, we need to find its mass before we can figure out the molecular formula. So the mass of a carbon is 12, and there's only 1 of them. The mass of a hydrogen is 1, and there are 3 of them. So 12 times 1 and 1 times 3, this is going to be 12 plus 3 is 15. So that means that the mass of one of the building blocks is 15. But the mass of the molecule is 45. So 45 divided by 15 gives me the number 3. That tells me that there are 3 building blocks, or 3 units of CH3 in the molecule whose mass is 45. I need to multiply all of the subscripts in CH3 by a 3 to get to this mass. So C times 3 is going to be C3, and then H3 times 3 would be H9. So this is my final answer. Okay, last question. The empirical formula is CH2. Remember, carbon's mass is 12, and there's only 1 of them. Hydrogen's mass is 1, but there are 2 of them, which gives me an empirical mass of 14 AMU. However, the molecule has a mass of 28. So if I take the mass of the molecule and divide it by the mass of the empirical unit, I get the factor 2. That means that there are 2 units of CH2 in this molecule. So I'm going to take this 2 and multiply it by the subscripts in the formula, and I will get a final answer of C2H4, because I multiplied both by 2. So I made some edits to the formatting, but you need to copy down these pair-up questions underneath the Do Now on your classwork page. And finally, I want you to copy down these summary questions underneath the pair-up. We finished the lesson. Congratulations. Thanks for watching, and I'll see you tomorrow.